The third model from Key et al. Utilizes fuzzy overlay as the decision rule to transform the candidate set into the decision set. And we'll see what fuzzy means in this context and why it's a better way to go about modeling site suitability. So Kudzu requires a certain minimum annual precipitation. We know that. It needs a long growing season and a mild winter, as well as proximity to existing Kudzu growth. So these are all important, but we don't see any hard lines here. There's no certainty to what temperature, what precipitation, etc. So these are uncertain and imprecise rules for Kudzu. But the rigid thresholds that we use for annual precipitation, frost-free days, in both the linear combination, the weighted linear combination, and the Boolean layers, the Boolean decision rules, to define suitability, we know those are unreasonable or unrealistic because such hard, precise cutoff points don't exist in reality. Let's say between 1499 and 1500 millimeters of precipitation. Fuzzy is a way to get around that, a way to model with uncertainty. So the factor standardization in fuzzy modeling is called fuzzification. So fuzzification is the process of converting an environmental value that we see here, like on the x-axis, to a fuzzified value, or what we call a membership value. And membership values always range between 0 and 1. And are proportions. The proportion of a particular environmental value that corresponds to the suitability for Kudzu establishment for a particular factor. So in this example here, we have two critical points in this fuzzy linear function, which is an increasing fuzzy linear function, or a stepwise increasing fuzzy linear function. So the critical point here is A, which is 100, and B, which is 200. And these define the very quick breaks in slope. So this region, 0 to 100, has a slope of 0. And so does this region from 200 onwards, also has a slope of 0. The difference being, of course, that between 0 and 100, the membership within or for Kudzu suitability is 0 here until 100 and 1 from 200 on. So this environmental value might be things like the growing degree days. In our case, the days greater than 0 degrees Celsius. So what it says is that once we're at 100, we still have no membership. So if there's 100 or less, so 100 or less degrees above 0 degrees Celsius, Kudzu cannot survive, even with all other factors being optimal. From 100 to 200, right here, we have this slope right here. This slope is constant, as you can see. It's just a straight line segment. And it's 1 divided by 200 minus 100. So in this case, 1 over 100 is the slope. Until 200, in terms of the environmental value, like number of days above 0 degrees Celsius. Then the slope is again 0. So with all other things being equal, once we're 200 days or over, in terms of frost-free days, that's fine for Kudzu. It can successfully, under those conditions of temperature, exist, reproduce, etc. The equation for this function is given here. So MF at x is just the lines that you see here, the green line. And here it specifies that it is 0 for x less than or equal to a. And again, a is 100 in our case. And then x minus a over b minus a for a, which is less than x, less than b, where a and b are 100 and 200. So x is anything between 100 and 200. Then it's 1 for all x values. Again, x values are the environmental values here, growing degree days, greater than or equal to b, which is 200 right here. So we have full membership at 200 and over, partial membership between 100 and 200, and no membership less than 100 in that direction. Where membership here is membership in suitability for Kudzu. And this is a commonly used function for fuzzification because it gives us this idea of uncertainty. Uncertainty exists between 100 and 200. So let's say at 150 growing degree days, we'll have approximately 0.5 as the membership value. So it's half suitable for the establishment of Kudzu if you have 150 growing degree days. Likewise, if you went to 175, you'd be up here at 0.75. And once you get to 200, well, you're way up here at 1. So 200 and over on this side are completely suitable for Kudzu, establishment, propagation, reproduction, existence, etc. So we transform growing degree days or any environmental value. And again, the values here on the x-axis for different environmental values will be different. So 100 and 200 are, in this case, picked specifically because of our knowledge of Kudzu and its relationship to growing degree days. If it's a different environmental variable, the x-axis won't be the same, and therefore a and b will not be 100 and 200. The a and b correspond to locations on the x-axis, and so they are specific to the range of the environmental value being fuzzified. Once it's fuzzified, then we have a layer which ranges for every cell between 0 and 1. And that becomes a fuzzy layer, or fuzzy factor. So Kudzu grows on all types of soils and slopes. So it's not sensitive to soil and slope like some plants are. But temperature and rainfall are the most relevant factors. And we have already average annual precipitation and number of growing degree days, as well as the existence of Kudzu, since Kudzu nearby is more likely to lead to more colonies of Kudzu through reproduction, whether that's vegetative reproduction or sexual reproduction. So if we look at a fuzzy overlay cartographic model, it would look like this. We would have our Kudzu at the bottom, and then we'd calculate something called the Euclidean distance, where every cell within our decision frame here is given a value according to how far that cell is from the nearest Kudzu observation. And so that process provides a layer which is the distance to Kudzu. And then we fuzzify that distance using a fuzzy linear function in what's called fuzzy membership to output a fuzzified factor. So this is our factors right here in this model. Then, with precipitation, fuzzy linear again, creating our fuzzy or fuzzified precipitation. And likewise with temperature, fuzzy linear to a fuzzified temperature, where temperature here means growing degree days above 0 degrees Celsius. Just easier to say temperature since that's the variable from which that was derived. Once we have our factors ready to go, then we have to decide what the decision rule is going to be. And with fuzzy factors, we use fuzzy logic, such as a fuzzy AND. A fuzzy AND takes all those in and outputs a prediction. Fuzzy AND looks for the maximum value for each cell across each of the fuzzified variables and outputs that maximum value. And that's how fuzzy AND is created, and in the end we have a predictive model based on fuzzy logic. So there's a degree of uncertainty there. The output of the model ranges between 0 to 1, like so, where 0 is unlikely habitat for Kudzu, and 1 is very likely habitat for Kudzu. Now, the way we use fuzzy linear functions can be in two ways. This is called a fuzzy decreasing linear function. So we have distance from Kudzu as an example. So as distance increases from Kudzu, we would expect that the probability for the establishment of a new colony is going to decrease as well. And as distance is smaller or decreases towards a Kudzu observation, we would expect an increasing probability or likelihood that we would have Kudzu establishing because of that proximity. So in this case, we have to come up with our critical values, A and B. And that's based on distance. And we're looking at a continental distance scale here, where this is in meters. So that's 0 meters, that's 500 kilometers, 1,000 kilometers, 1,500 kilometers, 2,000 kilometers. And so based on the Keyes model, they decided that the critical values would be 100,000, so that's 100 kilometers, and 1 million, 1,000 kilometers. So A, this critical value right here, is 100,000, and B, right here, is 1 million. And then the slope is negative between these two. Since we have full membership up to 100 kilometers, so that means if you're within 100 kilometers of an existing Kudzu colony, it will be very likely that Kudzu will spread from that colony to your location, all other things being optimal. Then, as we get more than 100 kilometers, we get less chances or less likelihood. So, for example, at 500 kilometers, well, that's not a very good straight line here, but at 500 kilometers, we would be around half or so of the likelihood. And once we get to 1,000 kilometers, we reach 0 likelihood. So at 1,000 kilometers, if a cell is 1,000 kilometers away, and again, a cell is part of will be part of the decision set eventually, so it has to be selected upon. And if that cell is, all other things being optimal, 100 or 1 million meters or 1,000 kilometers away, there would be no likelihood for establishment based on proximity to Kudzu, because it's just too far. Of course, a lot of that could depend on where you are. So we're assuming here we have what's called an isotropic process. And that means that this distance effect is the same in all directions. Whereas, let's say certain birds, migratory birds, eat Kudzu seeds, then we might have a much longer distance effect north to south because of migrating species than we do east to west. So there's all kinds of possibilities like that you could think of. But we're looking at isotropic processes, so we have the same effects in all directions with distance. So this then fuzzifies distance from Kudzu into a fuzzy membership value for Kudzu. In Python, the map algebra statement is pretty straightforward. We use the uke distance Kudzu, where our input is going to be our Kudzu layer. Our output will be cells that are 1,000 by 1,000 meters, and the distance will be assigned to each cell, plus or minus 500 meters to the nearest Kudzu observation, or plus or minus probably 1,000 meters to the nearest Kudzu observation. Even a little more than that if they're on the diagonal, right? So we get dist Kudzu, and we then have a distance layer, which you can see here is just categorized with orange all the way to purple. Purple is very far away. Pink is very far away too, and the bright orange are very close to existing Kudzu observations. Then we can convert that into a fuzzy membership value using fuzzy linear. So fuzzy linear, again, is a Python object that we create using the fuzzy linear function that you see right up at the top here. And because we want a decreasing fuzzy linear function, we specify the b and then a. And that ensures that we have a negative slope from a to b. Usually we specify a to b in here for increasing fuzzy linear functions, like we've seen as well. But for a decreasing one, we put the second point, b first and then a second. And that creates that function, and we call it here fuzz L. Then we use the fuzzy membership function, and we say the dist from Kudzu, whatever variable that is that represents this thing here. So that's the dist from Kudzu. And then we put in for the second parameter fuzz L, the fuzzy function. And that outputs what we see on the right here. Here we see a very continuous and continuously changing colors from dark red to yellow, white, and then to blue. Dark reds are near 1 and blues are near 0. So those are near zeros, and out here near approximately 1 with respect to the distance from a Kudzu observation and its likelihood for the establishment of Kudzu. So that's the fuzzification. And you'll see here it's just I'm showing the part of the cartographic model that we're doing within Python. So you can see the equivalencies. Total annual precipitation is opposite in terms of its fuzzy linear form to distance, because more precipitation is better for Kudzu. Kudzu likes it very wet. So we have total annual precipitation as our environmental variable on the x-axis here, and the fuzzy membership as usual on the y-axis between 0 and 1. And then we specify, based on Key et al.'s work, we have our A value A is 500 and B is 1500 millimeters. So those are millimeters there. So 500, oh, and it's actually 1750 up here, not 1500. So to 1750. So this is an increasing fuzzy linear function like the first one I explained, whereby we have some likelihood for the establishment of Kudzu, all other things being optimal, when we have precipitation of more than 0.5 meter per year. Once we get up to 1750, then we have full membership. So precipitations 1750 and above, or just above 1750, I should say, or actually at 1750, we'll have full membership in the fuzzy membership value for the establishment of Kudzu. We do a very similar thing for that in Python. First, we get our fuzzy linear again, but this time we go A, B in that order because it's an increasing linear function. So 500, 1750. And we use the fuzzy linear function and those parameters to get fuzz L here. Then into the fuzzy membership goes the precip. So that's our precip millimeters, and our fuzzy linear function. And that creates fuzzy PRE, which is the fuzzified precipitation. And it looks like the one on the right here, where dark reds are 1 and blues are 0, or very near 0 anyway. Some could be actually 0. Finally, the number of days above 0 degrees Celsius is also an increasing fuzzy linear function with these parameters, which are the ones I explained in the first example when I introduced you to what a fuzzy or fuzzification was with a fuzzy linear function. So there's nothing new to learn here. But we have A and B, 100 and 200, and we have to note that it's an increasing function. So we know what order to put these two parameters, these two values, in the fuzzy linear function in Python. Instead of doing it in Python, here's the tool, just showing a tool example. Our input raster is days greater than 0 degrees Celsius. We call the output temp fuzzy, and we specify the membership type, linear, minimum 100, and maximum 200. And we click OK, and that produces what we see on the right here. So the red areas are near 1, some very red areas will be actually 1, and the blues, yellows are not 1. They're get closer to 0. And there's the equivalent for Python. So fuzzy linear 100 to 200, and again that's order A, B for that particular fuzzy linear function. And then we do the same thing. We create temp fuzzy for temperature fuzzified, fuzzy membership, days greater than 0 degrees Celsius, and our fuzzy function in the second part here. Finally, we use fuzzy overlay in order to create our model. So to create the decision set, we use fuzzy overlay. And fuzzy overlay takes in two arguments. The first is a list of the names of the variables or layers in your table of contents. So in this case, we have a list object, again, the open bracket and close bracket, and then in there, we have things separated by commas. And that creates what's called a Python list. And in here, I have my fuzzDist, fuzzPre for precipitation, and temp fuzzy for temperature fuzzified. After we specify the input layers, and these are raster variables, each of these, so we have 3 raster variables. Then we say comma and what type of fuzzy overlay we want. And again, this is the decision rule here, and we go with fuzzy and, which is looking for the intersection, basically, of the different fuzzy layers. So our prediction then is right here, I should say. If we use something other than an and, like minimum, for cell statistics, that will produce the same thing. So the minimum across each layer for each cell location is recorded in the output. That's the same thing as a fuzzy and, is the minimum. value. And then we have our final model here, which is, again, ranging between 0 to 1, where zeros are out here, and in this case, 1s are going to be over here. And this is a much better model of the potential range for the establishment, reproduction, and existence of kudzu. For example, we see where we have a lot of lake effect temperatures, precipitation off of Lake Erie, off of Lake Ontario here, where we have these big green spots and red spots here, depending on the elevations and stuff that you find there, and red all up the coast and the south here. So this kind of makes more sense in terms of a potential map for the establishment of kudzu. Now the sensitivities of that, of course, are firstly the transformation functions. There are many forms. We used fuzzy linear here. In the exercise that is associated with this particular module, you will see other forms of fuzzy membership functions, like sigmoidal ones like that, called fuzzy large in this case. So the shape of that function, and it also has different parameters. This has AB, this has a midpoint and a spread. And other ones have different parameters. Well, if you change the fuzzy function, you will change the output model, or the predictive model, the decision set. Also, modifying the transformation parameters. So within the same set of functional graphs for fuzzification, like all fuzzy linear like we used, if we modify those critical values, A and B, well, that will also change our output significantly. So it's very sensitive. We have sensitivities to both of those things, the type of function and even the critical values within a function. And in the exercise, you'll do a sensitivity analysis by looking at how just the functional forms, if you change those, how much does that change your results? And so that's something you need to understand to find out whether or not you have robust results. Robustness comes when you have multiple methods or assumptions being tested through this modeling process and having the approximately same predictions. And that means you have something which is fairly robust in terms of a model. So in summary, we have what we can look at here, linear combination versus fuzzy overlay. So linear combination required reclassification into an ordinal scale, and that means defining very precise class breaks to transform our environmental variables or factors into a common scale of 1, 2, and 3. Why 1, 2, and 3? Why not 1 to 10 or 1 to 100? It becomes hard sometimes to justify those choices with a direct linear combination. But it's often a good first approximation to get an idea generally of what results might look like with a more robust or a model that's slightly better suited for the conditions you're looking at. Then we apply linear functions for overlay. So we use plus and then layer times weight. X, like if the layer is X times the weight for that layer, W sub I. And we apply weights to individual factors for linear combinations. So we can apply weights. We can also apply weights in fuzzy as well if you want. That's also valid. With fuzzy overlay, instead of reclassification, we have fuzzification. And that we don't determine class breaks, we define a membership function. So it defines a range of values over which membership can occur in the suitability for Kudzu. And instead of applying a linear function as the decision rule, we apply a fuzzy overlay. In our case, we use a fuzzy and. You can try it with a fuzzy or, for example, to see the difference. So in the exercise 4, what you'll be doing is using climate data in what's called a net CDF format to model the potential for kudzu establishment in Ontario. You'll be able to extract MAP, which is the mean annual precipitation, and NFFD, the number of frost-free days. As well as you will produce your own layer showing where kudzu is, and it tells you where to put that kudzu observation in the exercise. And you'll use fuzzy membership or fuzzy logic to undertake that modeling process to find out which areas in Ontario under a future climate scenario, which these are coming from, would be good places for the establishment and propagation of kudzu. So things to look out for in the future. In our case, 2080 is the year for the data that is provided.